Welcome to another deep dive. Ever wonder how 8 million species fit on this one planet?
It's a question that has puzzled ecologists for centuries.
And today, we're going to explore it using a fascinating chapter from a Spanish ecology book.
The book is called, well, in English, it's How to Fit 8 Million Species on One Planet.
Catchy title. But seriously, we're going to delve into some groundbreaking discoveries and theories that attempt to answer that very question.
We'll be tracing the history of ecological thought, starting with the foundations laid by Charles Darwin and his theory of evolution by natural selection.
Right, Darwin's observations on the Galapagos Islands revolutionized our understanding of how life diversifies.
Absolutely, those finches with their beaks perfectly adapted to different food sources. A classic example of evolution in action.
Yeah, it's like nature's way of saying adapt or perish.
Exactly, and those subtle variations over generations can lead to the formation of entirely new species.
It's mind-boggling to think that the incredible diversity of life we see today arose from these tiny incremental changes over millions of years.
It really highlights the power of evolution as a creative force, constantly shaping and reshaping the tapestry of life.
Okay, so evolution explains how species arise, but what about where they end up?
Hmm.
That's where biogeography comes in, right?
You got it. And one of the pioneers of biogeography was Alfred Russel Wallace, a contemporary of Darwin.
Wallace was obsessed with mapping species distributions, and in doing so, stumbled upon a fascinating puzzle, the Wallace line.
Ah, yes, the Wallace line. Imagine sailing through the islands of Indonesia and suddenly encountering a completely different set of mammals, despite no obvious physical barriers separating the islands.
Wait, what? How is that even possible? It sounds like something out of a fantasy novel.
It's a real phenomenon. It turns out that the depths of the seabed, those submerged areas that were once land bridges, hold the key to this mystery.
Okay, so these ancient land bridges allowed some species to cross while others were prevented from doing so.
Exactly. Those differing depths acted as selective filters, leading to distinct evolutionary paths on either side of the line.
Wow, it's like a glimpse into the deep history of our planet, revealing how past geological events can have a lasting impact on where species live today.
And understanding these patterns helps us to predict where certain species might be found and how they might respond to environmental changes.
So biogeography is like a detective story, piecing together the clues to understand how life came to be distributed across the globe. But let's shift gears a bit and think about how we even begin to count the millions of species inhabiting Earth.
That's a daunting task. Early ecologists like Olaf Arrhenius, who studied plant diversity on islands near Stockholm, provided some key insights.
Arrhenius, right. He found that the number of species on an island is related to its size. Larger islands, more species. Makes sense.
It's a fundamental principle in ecology. Larger areas typically offer more diverse habitats and resources, supporting a wider range of species.
It's like saying a sprawling city can support a greater variety of businesses than a small town. More space, more opportunities.
Exactly. And this principle applies not only to islands, but to ecosystems on continents as well.
Okay, so island size influences species richness. But what about the relative abundance of those species? Are they all equally common?
Well, that's where the work of Isamoto Mura comes in. He studied the distribution of species in various ecosystems, particularly focusing on intertidal zones.
Intertidal zones are those areas along the coast that are submerged at high tide and exposed at low tide.
Exactly. Motomura found that in any given community, a few species tend to be very abundant, while most are quite rare.
Ah, so it's not a uniform distribution, it's more like a popularity contest with a few superstars stealing the show.
It's a pattern that ecologists have observed across a wide range of ecosystems, from tropical rainforests to coral reefs.
So to understand biodiversity, we need to consider not only the number of species present, but also how many individuals of each species exist.
Precisely. We need to understand both species richness and species abundance.
Okay, this is starting to paint a more nuanced picture of biodiversity. It's not just about a simple head count. It's about understanding the dynamics and distribution of species within a given area.
Absolutely. And these ideas about island size, species richness, and abundance patterns all come together in a fascinating theory called island biogeography.
Okay, island biogeography. That sounds intriguing. I'm all ears.
Imagine a group of islands, each a blank slate waiting to be colonized by species from a mainland source.
So it's like a race to establish a foothold on these pristine islands.
In a way, yes, but the success of colonization depends on several factors, including island size, distance from the mainland, and the carrying capacity of the island.
Carrying capacity, meaning the maximum number of individuals an island can support.
Precisely. Think of it like this. Larger islands are like bigger targets. They're more likely to be reached by dispersing species.
That makes sense. It's like if you're throwing darts at a dartboard, you're more likely to hit a larger target than a smaller one.
Exactly. But distance also plays a role. Islands closer to the mainland have a steady stream of new arrivals, while those farther away face greater challenges in establishing new populations.
So it's a balance between the rate of immigration, those new arrivals, and the rate of extinction, those species that fail to survive on the island.
You're getting it. And this balance, over time, leads to a dynamic equilibrium where the number of species on an island remains relatively constant.
So it's not a static system. It's constantly in flux, with new species arriving and others disappearing.
Exactly. And to test these ideas, ecologists Daniel Simberloff and E.O. Wilson conducted a bold experiment. They fumigated small islands, eliminating all the arthropods.
Wait, they wiped out all the insects and spiders on these islands? That seems a bit drastic.
It was a controlled experiment to see how those islands would be recolonized. What they observed was remarkable.
So, like hitting the reset button on the ecosystem and watching how life reclaims its territory.
Exactly. The recolonization patterns closely matched the predictions of the theory. Islands closer to the mainland and those larger in size bounced back faster, accumulating species at a predictable rate.
Wow. So their experiment provided strong evidence that the principles of island biogeography were at play in the real world.
It was a groundbreaking study that revolutionized our understanding of how species colonize and persist on islands. And these principles, while developed in the context of islands, have broader applications for understanding biodiversity in fragmented landscapes on continents as well.
So it's like a microcosm of what's happening in larger ecosystems that are becoming increasingly fragmented due to human activities.
Exactly. It highlights the importance of habitat connectivity in maintaining biodiversity.
Okay, this is all starting to make sense. We've gone from Darwin's finches to biogeography, island size, and now this fascinating concept of island biogeography. It's all starting to fit together. But if we zoom in from islands to the level of individual species, how do we understand how so many different species manage to coexist in the same area?
That's where the concept of the ecological niche comes in. Each species occupies a unique niche, defined by its interactions with the environment and other species. Think of it as a species' role or profession in the ecosystem.
So it's not just about where a species lives, it's about what it does, how it makes a living, and how it interacts with its surroundings.
Precisely. The concept of the niche has evolved over time, from Joseph Grinnell's focus on the physical environment to Charles Elton's emphasis on biotic interactions.
So Grinnell was all about the abiotic factors, the non-living components like climate and soil, while Elton brought in the biotic factors, those interactions with other living things.
You got it. And later, G. Evelyn Hutchinson expanded the niche concept even further, envisioning it as a multidimensional space.
Okay, multidimensional space. My brain is starting to hurt a little. Can you explain that in simpler terms?
Imagine a graph where each axis represents a different environmental variable, like temperature, humidity, or food size.
Okay, I'm picturing it now. So each species occupies a specific point in this multidimensional space, defined by its unique combination of tolerances and requirements.
Exactly, and this concept helps us understand how so many species can coexist in seemingly limited environments. They avoid direct competition by specializing in different ways, dividing up the resources and opportunities available.
It's like a giant ecological jigsaw puzzle, with each species fitting into a unique piece of the overall picture.
Precisely. But this raises a perplexing question that has puzzled ecologists for decades. How can so many plankton species coexist in the seemingly uniform environment of the open ocean? It's a question that challenges our understanding of niche partitioning and competition.
That's right. It's been called the paradox of the plankton. How can so much diversity exist in a habitat that appears so homogeneous? There must be more to the story than meets the eye.
Absolutely. To unravel this paradox, we need to consider the subtle ways in which plankton species differ in their resource use and life histories.
Okay, I'm ready to dive into the world of plankton and explore how they manage to carve out their niches in this seemingly uniform environment. But before we get too deep into those tiny creatures, let's take a step back and think about another key ecological concept: competition.
Competition, that's right. It's a fundamental force in nature, driving the struggle for survival and shaping the distribution and abundance of species.
Okay, competition, survival of the fittest. But how does competition play out in the complex world of ecological communities? How do we even begin to study and understand it?
Well, one approach is to look at simple, well-defined systems where we can manipulate variables and observe the outcomes. One classic example is the work of G.F. Gauss, a Russian ecologist who studied competition between different species of paramecium.
Paramecium, those tiny single-celled organisms that swim around in pond water.
Exactly. Gauss's experiments provided some key insights into the principles of competition and coexistence. Gauss grew these paramecium in test tubes, providing them with a limited food supply.
So like a tiny controlled ecosystem.
Exactly. And what he found was that when two species with very similar resource requirements were grown together, one species inevitably outcompeted the other.
Ah, the classic competitive exclusion principle. Two species can't occupy the exact same niche. One will always be a better competitor, driving the other to extinction.
Precisely. But Gauss also found that if he introduced some environmental variation, like changing the nutrient supply, both species could coexist.
So by adding some complexity to the environment, those paramecium were able to carve out slightly different niches, allowing them to coexist.
Exactly. This highlights the importance of niche differentiation in promoting biodiversity. Even subtle differences in resource use or habitat preferences can allow multiple species to share the same environment.
It's a reminder that nature is rarely black and white. There are always shades of gray that allow for incredible diversity to flourish.
And these interactions between species extend beyond competition to include predator-prey relationships, those fascinating dynamics where one species hunts and consumes another.
Oh yeah, predator-prey relationships. Those classic nature documentaries with the dramatic chase scenes. But when I think about food webs, those diagrams with arrows pointing everywhere, it seems a bit chaotic. How can we make sense of that complexity?
While it might appear chaotic at first glance, there are underlying principles that govern those interactions. To decipher them, we can turn to the work of Alfred Lotka and Vito Volterra.
Lotka and Volterra.
These brilliant mathematicians developed equations to model predator-prey dynamics, predicting cyclical patterns in their populations.
The cyclical patterns, meaning the populations go up and down in a predictable way.
Exactly. Imagine a scenario where prey populations are abundant, providing plenty of food for predators.
Okay, so the predators thrive and their numbers increase.
Precisely. But as predator numbers rise, they consume more prey, causing the prey population to decline.
Ah, so then the predators start to run out of food.
Exactly. And as the predator population declines, it gives the prey population a chance to recover.
And then the cycle starts all over again. It's like a never-ending game of ecological tag.
You've got it. And these cyclical dynamics have been observed in many real-world ecosystems. A classic example is the Isle Royale study.
Isle Royale, that island in Lake Superior with the wolves and moose.
Exactly. Researchers have been tracking wolf and moose populations on Isle Royale for decades, observing fluctuations that resemble those predicted by the Lotka-Volterra model.
So those mathematical equations weren't just theoretical constructs. They reflected real-world ecological patterns.
It's a remarkable example of how mathematical models can help us understand and predict the dynamics of complex natural systems.
Okay, so the Isle Royale study is a simplified representation of predator-prey relationships. But I'm guessing real-world ecosystems are much messier, with multiple predator species, diverse prey options, and ever-changing environmental conditions.
You're absolutely right. Real ecosystems are incredibly complex and dynamic. But even within that complexity, the concept of top-down control, where predators regulate prey populations, remains a crucial ecological principle.
Top-down control. Can you elaborate on that?
Top-down control means that changes in predator populations can cascade through the food web, influencing the abundance and diversity of other species.
So, by controlling the numbers of their prey, predators can indirectly influence the structure of the entire ecosystem.
Precisely. And this brings us to another fascinating concept: keystone species.
Oh yeah, keystone species. Those species that have a disproportionate impact on their ecosystem, even if they aren't the most abundant.
Exactly. Think of them as the ecological linchpins that hold everything together. Removing a keystone species can have dramatic consequences for biodiversity, potentially leading to a simplified ecosystem with fewer species.
Okay, I'm intrigued. Could you give me an example of a keystone species?
Sure. A classic example is the starfish Pisaster ocratius, which inhabits the rocky intertidal zones along the Pacific coast of North America.
Starfish, those five-armed creatures that cling to rocks. How could they possibly be keystone species?
Don't be fooled by their seemingly passive lifestyle. These starfish are voracious predators, feeding on mussels, barnacles, and other invertebrates. And ecologist Robert Payne conducted an experiment that demonstrated their crucial role in maintaining diversity.
Okay, what did he do?
Payne removed starfish from some experimental plots in the intertidal zone while leaving others undisturbed as controls.
So like creating a starfish-free zone to see what would happen.
Exactly. And the results were striking. In the plots where starfish were removed, mussels, which are strong competitors, quickly took over, crowding out other species.
So the starfish, by keeping the mussel population in check, were actually promoting diversity.
Precisely. Without the starfish, the ecosystem became dominated by a single species, leading to a decline in overall diversity.
That's incredible. It really highlights the interconnectedness of nature and how even seemingly insignificant creatures can play crucial roles in maintaining balance.
And this concept of keystone species has major implications for conservation. Identifying and protecting these critical players is essential for maintaining healthy and resilient ecosystems.
It makes you wonder how many other keystone species are out there, quietly shaping the world around us.
It's a fascinating question, and as we delve deeper into the mysteries of biodiversity, we'll continue to uncover the hidden connections and surprising roles that different species play in maintaining the delicate balance of life.
We've talked about competition and predation, but what about those win-win situations in nature, where species benefit from each other's presence?
You're bringing up a crucial point. We can't overlook the importance of mutualistic relationships, where both species involve benefit. These interactions, often overlooked in favor of more dramatic stories of competition and predation, are essential for the functioning of ecosystems.
Okay, I'm all ears. Tell me about some of these fascinating mutualistic relationships.
One of the most well-known examples is the relationship between flowering plants and their pollinators.
Oh yeah, the classic image of bees buzzing from flower to flower, collecting nectar and spreading pollen.
Exactly. It's a beautiful example of mutual benefit. The plants provide the pollinators with food in the form of nectar and pollen, while the pollinators help the plants reproduce by transferring pollen from one flower to another.
It's a perfect partnership. But I bet there's a lot more to this story than meets the eye.
You're right. The understanding of this relationship has a fascinating history, dating back to ancient Greek naturalists who observed bees collecting nectar from flowers. However, it wasn't until the mid-18th century that Arthur Dobbs, an Irish naturalist, made the crucial connection between bees and pollination.
So before Dobbs, people didn't realize that bees were playing a vital role in plant reproduction.
It's hard to imagine now, but yes. Dobbs observed bees transferring pollen between flowers and recognized its role in fertilization, leading to the production of seeds and fruits.
That's a pretty big deal. And it seems so obvious now, but it took a keen observer to connect the dots.
It's a reminder that even seemingly simple observations can lead to profound insights. And Charles Darwin, with his fascination for orchids and their intricate pollination mechanisms, further illuminated the co-evolutionary dance between plants and their pollinators.
Co-evolutionary dance, what does that mean?
It means that over millions of years, plants and their pollinators have evolved together, each adapting to the other's needs and behaviors.
So they've shaped each other's evolution, becoming increasingly specialized and interdependent.
Precisely. And this co-evolutionary process has resulted in some truly remarkable adaptations, from the long tongues of hummingbirds that perfectly match the shape of certain flowers, to the intricate traps of orchids that lure specific insects to ensure pollination.
It's a testament to the power of natural selection and the incredible diversity of life on Earth.
Indeed. We've covered a lot of ground, from competition and predation to these amazing mutualistic relationships. But as we continue to unravel the mysteries of how 8 million species fit on this planet, we need to consider another key factor: density dependence.
Density dependence. I'm not familiar with that term. Can you explain what it means and how it relates to biodiversity?
Density dependence refers to the idea that the strength of ecological interactions, such as competition or predation, can depend on the density of the populations involved.
So the more crowded a space becomes, the more intense the competition for resources. Kind of like rush hour traffic.
That's a great analogy, and this principle helps explain the high tree diversity often observed in tropical forests. The Jansen-Connell hypothesis suggests that being too common can be a disadvantage for seedlings.
Too common? How could that be a bad thing?
Imagine a scenario where a tree produces an abundance of seeds that fall directly beneath the parent tree. Those seeds are likely to be targeted by seed predators or pathogens that specialize on that particular tree species.
Ah, so those seeds are like sitting ducks.
Exactly. But seeds that are dispersed farther away from the parent tree have a better chance of escaping those enemies.
So being rare, in this case, can be an advantage.
Precisely. It reduces the risk of being targeted by specialized predators or pathogens. And this principle applies beyond just trees to many other species. Being rare can provide a refuge from competition, disease, and predation.
It's like a game of hide and seek, where blending in and being less conspicuous can be a winning strategy.
That's a great way to think about it. Density dependence plays a vital role in shaping community structure and maintaining diversity. It's about finding that sweet spot where a species can thrive without becoming so abundant that it triggers negative feedback loops.
Okay, this is all starting to make sense. We've explored a lot of fascinating concepts today, from island biogeography to keystone species and those intriguing mutualistic relationships. But I have to admit, my brain is feeling a bit overloaded. I think it's time to take a break and let all this information sink in. We'll pick up our deep dive in the next episode and explore some even more mind-boggling ideas about how biodiversity is generated and maintained on Earth. Stay tuned. Okay, so last time we were talking about density dependence and those tiny little seedlings trying to make it in the big bad forest. It's like a jungle out there.
It really is. And as we continue our deep dive into biodiversity, we need to shift our focus a bit, expanding our perspective to consider the importance of space and time.
Okay, space and time, like the final frontier.
You could say that. Think about it this way. Instead of looking at a single snapshot of a community, imagine watching a dynamic video where we see how populations change and interact across both space and time.
Okay, so it's like those time-lapse videos where you see plants growing and changing over a season, except we're talking about entire populations and how they move and interact across the landscape.
Exactly. A great example of this is Carl Huffaker's work with those orange-loving mites. Remember those?
Oh yeah, the mite experiments. He created these little miniature worlds using oranges as habitats for these mites.
Precisely. And he found that when those mites were confined to a single orange, the predator mites quickly wiped out their prey, leading to the collapse of both populations. But when he introduced multiple oranges spaced apart, things got a lot more interesting.
So by simply adding more oranges and creating some distance between them, he changed the entire outcome for these mite populations.
Exactly. The spatial separation of those oranges, those little habitat patches, allowed the prey mites to disperse, find temporary refuge, and avoid being completely wiped out by the predators. It created a more dynamic and resilient system.
It's like a game of ecological leapfrog. The prey mites were always one step ahead, searching for new territories, while the predators were in hot pursuit.
That's a great analogy, and this highlights the importance of habitat connectivity, those corridors and pathways that allow species to move and disperse across the landscape. Fragmentation, whether by natural barriers or human activities, can disrupt these vital connections, isolating populations and making them more vulnerable to extinction.
It's like building roads through a forest, dividing a once continuous habitat into isolated islands. It makes sense that those isolated populations would have a harder time interacting, finding mates, and adapting to change.
Precisely. And this brings us to the concept of metapopulations, interconnected populations of the same species that exchange individuals through dispersal. Think of it like a network of populations, some thriving as sources, producing excess individuals that disperse to other populations, while others struggle as sinks, relying on those immigrants to persist.
This reminds me of those source and sink dynamics we discussed earlier in the context of island biogeography. So some populations are like strongholds, sending out reinforcements to those struggling on the periphery.
You're right. Many ecological principles apply across different scales and systems. A great example of metapopulations is Ilkka Hansky's long-term study of the Glanville fritillary butterfly in Finland. He tracked these butterflies across thousands of meadow patches, some large and lush, others small and less favorable.
Finland, huh? Okay, so what did he find out about these butterflies?
Hansky discovered that those butterfly populations in the high-quality meadows acted as sources, producing a surplus of individuals that dispersed to the less suitable sink habitats. This influx of immigrants helped prevent those sink populations from disappearing altogether, demonstrating the importance of connectivity and those source-sink dynamics in maintaining the overall persistence of the species.
Wow, it's amazing how these different populations rely on each other for survival. So even in a fragmented landscape, as long as there are some healthy source populations and those connections are maintained, there's hope for those struggling populations on the fringes.
Exactly. And this highlights the importance of considering not just individual populations, but the entire metapopulation network when developing conservation strategies.
Okay, so we've talked about evolution, biogeography, competition, predation, mutualism, density dependence, and now these dynamic metapopulations. Throughout our deep dive, we've been focusing a lot on how species adapt and interact, but what about the role of chance in all of this? Does luck play a part in shaping ecological communities?
That's a great question. It brings us to Stephen Hubble's neutral theory, a provocative idea that challenged traditional ecological thinking by suggesting that species differences might not be as important as we once thought.
Wait, so all those intricate adaptations, those finely tuned niches, might not be the driving force of biodiversity?
Hubble proposed a simplified model where all species are treated as ecologically equivalent, meaning they have similar birth rates, death rates, and dispersal abilities. In this model, it's random events like dispersal that determine which species end up where and how abundant they become.
So it's like a giant ecological lottery, where luck, rather than fitness, determines who wins and who loses. That's a pretty radical idea.
It is. And while neutral theory might not perfectly capture the complexities of the real world, it forces us to acknowledge the role of chance and stochasticity in ecological processes.
So it's not always about being the fittest. Sometimes it's just about being in the right place at the right time, or maybe just being lucky.
Exactly. And to really see how chance and history can intertwine to shape biodiversity, consider the fascinating story of how monkeys arrived in South America. Millions of years ago, a small group of monkeys somehow made the incredible journey across the Atlantic Ocean from Africa to South America.
Monkeys rafting across the Atlantic. That sounds like a tall tale.
It does, but the evidence suggests that it actually happened. Those monkeys, clinging to a floating raft of vegetation, somehow survived the perilous journey and established a new population in a land where their kind had never existed before. And from that single improbable event, the entire radiation of South American monkeys arose, with over 139 species thriving today.
It's mind-blowing. A random event, a lucky drift across the ocean, could have such a profound impact on the course of evolution.
It really highlights the power of historical contingency in shaping the diversity of life on Earth.
Okay, so we've explored evolution, biogeography, competition, predation, mutualism, density dependence, metapopulations, and even the role of chance. With all this knowledge under our belts, can we finally answer that initial question? How do 8 million species fit on one planet?
It's a complex question with no easy answer, but we can point to a few key factors. First, evolution, driven by various mechanisms like natural selection, sexual selection, and genetic drift, is the ultimate engine of diversification. It's a continuous process of adaptation, innovation, and the emergence of new species.
So it's like an endless dance, with life constantly adapting and evolving to fill new roles and take advantage of new opportunities.
Exactly. And second, the Earth's incredible environmental heterogeneity, that vast array of habitats, climates, and resources, provides the stage for this evolutionary play to unfold.
It's like having a giant ecological playground, with endless possibilities for specialization and diversification.
Exactly. Third, the intricate web of interactions between species, those fascinating relationships of competition, predation, mutualism, and more, shapes community structure and drives both diversification and coexistence.
It's a reminder that it's not just about individual species. It's about those intricate connections, those relationships that bind species together in a grand ecological tapestry.
You got it. And finally, we can't forget the element of chance, those random events that can have a profound and lasting impact on the course of evolution, as we saw with those intrepid monkeys crossing the Atlantic.
It's a humbling thought, realizing that even in a world governed by natural laws, there's always an element of unpredictability, a wild card that can reshape the game.
Absolutely. And this understanding of how biodiversity is generated and maintained is not just an academic exercise. It has profound implications for conservation. In a world facing unprecedented environmental challenges, from climate change to habitat loss, we need to use this knowledge to protect the intricate web of life that sustains us.
So what are the key takeaways we should carry with us from this deep dive? Why does biodiversity matter?
We need to remember that biodiversity is not just about numbers. It's about the intricate interplay of evolution, ecology, and chance that has produced this incredible tapestry of life. And maintaining high biodiversity is crucial for ecosystem resilience. The more diverse an ecosystem is, the better it can withstand disturbances and continue to provide those essential services we rely on, like clean air, clean water, and food.
So it's like having a diversified investment portfolio.
Right.
The more diverse it is, the less vulnerable it is to market fluctuations.
That's a great analogy. And just like a financial advisor might recommend diversifying your investments, as ecologists, we urge everyone to appreciate and protect the diversity of life on Earth.
It's a call to action, a reminder that we're not just passive observers. We're active participants in shaping the future of life on our planet. So what can we do as individuals and as a society to protect this precious biodiversity?
It's about taking a holistic approach, recognizing the interconnectedness of life and the ripple effects of our actions. We need to reduce our environmental footprint, mitigate climate change, protect and restore habitats, and make conscious choices that support sustainable practices.
It sounds like a daunting task, but it's also an inspiring one, knowing that we have the power to make a difference.
It is. And as we wrap up this deep dive, I want to leave you with this thought. If a single improbable event, like a monkey raft drifting across the Atlantic, can reshape an entire continent's biodiversity, imagine the potential we have through our choices and actions to influence the future of life on Earth.
That's a powerful image to ponder. Thanks for joining us on this incredible journey through the world of biodiversity. It's been an eye-opening experience exploring those intricate connections and the remarkable resilience of life on Earth. Until next time, keep exploring, keep questioning, and keep diving deep.